Welcome everyone to today's Distributed Generation Integration Collaborative, or DGIC, webcast. Thanks for joining us. I'm Nadav Enbar. I'm a Principal Project Manager at the Electric Power Research Institute, EPRI, and your moderator for today's proceedings. I'm joined by several colleagues from both EPRI as well as the National Renewable Energy Laboratory, NREL, and together we're going to lead a discussion about the concepts of dynamic hosting capacity and flexible interconnection of distributed solar photovoltaics. Before we get started, a few words on logistics. We're going to take the webcast to 4 o'clock Eastern, 1 Pacific, so for about an hour. And really the aim is for us to present material to you for about 45 minutes and then to open it up for question and answer towards the end. We do have your lines muted to reduce background noise for the presentation component of the webcast, but we do encourage you throughout the webcast to use the WebEx console if you have a question, and we will try and get to those questions as much as we possibly can, time permitting. If you do submit a question using the webcast console, please submit it to everyone as the option. That way we'll make sure that we can gain access to it. We'll also unmute the phones at the end of our presentation should others want to pose a question verbally. And then, as is our practice, we will be posting both the webcast deck as well as a recording of today's webcast, both on the DGIC website. You can see the URL there, as well as epri.com. One further note, though. We are recording this webcast for posterity, so if you do not consent to being recorded, we appreciate you ending your participation now. Okay, so with that, before jumping into the particulars of today's webcast, I also want to briefly plug the Distributed Generation Integration Collaborative, which is sponsoring this webcast. For some of you who may not know, the DGIC was launched in 2013 as part of the U.S. Department of Energy's Sunshot Initiative, and it's really intended to serve as a platform, really, for exchanging information on a range of DER integration issues, innovative solutions that have been implemented and tried out, as well as evolving practices and processes related to the integration of distributed energy resources into principally distribution. In 2019, EPRI took over management of the collaborative from NREL, and we've expanded its purview beyond DER interconnection topics now to also include insights on DER business models and economics, as well as some regulatory considerations, as well as on technologies and methods for mitigation in terms of mitigating those impacts of DER on distribution. So what we're doing is in support of that of the core aims that the collaborative is intended for. We want to run a number of issue-oriented webcasts such as today's over the course of the calendar year. We're also going to be organizing a couple of in-person workshops. For example, last year we ran an energy storage interconnection workshop to discuss and work through identified challenges there, as well as issue reports and white papers and facilitate access to active working groups. For example, there are working groups that the DGIC sort of funnels interested parties to related to DERMS and energy storage integration. I encourage you guys to visit the recently redesigned website to access refreshed content. You can see the URL in the upper right-hand corner of this slide. And you can also sign up for DGIC newsletters to stay connected. And we're also interested in your feedback in terms of the kinds of research inquiries you would like the DGIC to pursue in the future. So just want to thank you in advance for your interest, and let's get rolling with today's topic. So by way of background, at a kind of 50,000 foot level for flexible interconnection, you know, this is really a novel approach that differs from traditional firm interconnection. And the principal differentiator here is that it applies controls to curtail DER. We'll be focusing on solar PV today, but DER output during grid-constrained periods of time, and that really enables greater amounts of DER to be interconnected to the grid without necessarily requiring an upgrade or associated mitigation to interconnect that DER. But it also changes the economic equation for DER asset owners as well as grid operators. So that's really kind of a starting point, and we'll be delving further into the definition of the concept of flexible interconnection, as well as talking through its mechanics throughout the course of this webcast. So what is it going to look like? So over the course of about the next 40 or so minutes, we want to go further into the ideas of what flexible interconnection entails, as well as the impact on the hosting capacity equation, moving to more of a dynamic orientation, getting into case studies of the application of the flexible interconnection concept, identify challenges and next steps, and then giving you a sense, a taste really, of some of the ongoing work that's in play both at EPRI as well as NREL. So at this point, I'd like to hand the microphone to Kelsey, who is a lead researcher, Kelsey Horowitz, who is a lead researcher at NREL, who will kick us off into the ideas of dynamic hosting capacity. Kelsey.
Thanks very much, Nadav. So before we really get into flexible interconnection, I just want to introduce the concept of this idea that constraints on the distribution system are really time varying in nature, and that'll lead into why flexible interconnection could be a solution that makes sense. Next slide. So if you think about traditional concepts of hosting capacity, they're usually based on snapshot analysis and a few time points or power flow scenarios throughout the year that are sort of worst case scenarios. But in reality, the amount of solar that can be hosted on the grid changes second by second, minute by minute, depending on the specific conditions around solar radiance and the load on the system, as well as potentially configuration of different devices there. And so this concept of dynamic hosting capacity is really about trying to look at the time series way that the grid is affected by these resources, and then understanding how frequently you have excursions outside of acceptable operating limits for the grid, how severe those excursions are, and what their duration looks like, in order both to understand, is there a way that we could implement a flexible interconnection strategy that reduces the output of the devices during a few periods of the year and then enables a large increase in the hosting capacity without severely impacting the economics of those PV systems, as well as just trying to understand and kind of recognize some of the uncertainty around traditional hosting capacity analyses and the inability to really nail down how much you can host using these traditional methods, and given the fact that a lot of times in distribution systems you have a lack of data about, for example, secondary networks or the value of each individual load. So if you threshold at sort of a very specific level in terms of what voltages you allow on the system or how much overloading you have, you may be conservative or limited by the quality of your data there. And in reality, that's a very short violation that won't really affect the system, or potentially isn't even there, depending on what the error in your data looks like at that particular time point. So I think just trying to kind of recognize that there are these dynamic limits on the grid is really important as a first starting point for thinking about flexible interconnection. Next slide. And we've done some analysis here at NREL trying to look at, even without flexible interconnection, what if you use a concept of these time varying constraints on the grids and a more duration and severity based definition of hosting capacity that acknowledges the fact, for example, that it's okay to be outside of AMCA range sometimes for some customers, as long as it's not really pervasive throughout the year and for all customers, or that you can temporarily overload lines and transformers without causing issues as long as the overloading is not too severe. We've seen that you can actually get, in some cases, a significantly higher fraction of PV hosted and probably still have everything be okay on the grid, even without adding that kind of dynamic control of the PV devices on the system. Next slide. So I think that'll kind of lead into this concept that I'll hand off to Stephen for, of trying to understand what is flexible interconnection if we want to combine this concept of time series constraints with active control of the PV devices to resolve those constraints. So I'll hand it off to Stephen here.
Thanks, Kelsey. If we can go to the next slide. Let's take a look at applying this concept of dynamic hosting capacity, or really the recognition that grid constraints are time varying, and how flexible interconnection really fits into this. So this is an illustration of what your time varying grid constraints might be, or some sort of export limit at a given site over the course of a year, and our traditional fixed capacity limit that may be, as Kelsey said, based off of kind of a worst case condition that may occur infrequently throughout the year. And so PV output based on that fixed capacity limit may be limited, but may not actually ever exceed that time varying grid constraint, just given the conservative nature of the way we typically do firm connections. If you advance one more, and the concept of flexible interconnection is being able to provide additional visibility and control into those time varying grid export limit conditions, and curtailing solar in this case infrequently throughout the year. So in this illustrative example, there was a 60% increase in PV capacity above that fixed capacity limit, with very limited energy curtailment throughout the year. You can see these couple example days. There are a few instances in the middle of the day on the first day where curtailment occurred, but the second day the grid export limits may have been higher, allowing for full production. So if you advance one more, this is really just to show that curtailment based on these time varying constraint periods can be minimal, and that you can enable more DER generation capacity while operating the grid within acceptable limits, assuming the appropriate visibility and control is in place. Next slide. So if we boil down what is flexible interconnection, it's really arrangements that enable more DER capacity to interconnect by using controls to manage the real power of DER and stay within those grid level constraints that are time varying. And this is an illustration I would like to show. So on the x-axis shows growing amounts of DER capacity on the grid, and the y-axis is the amount of production from that DER. And so we typically operate in this kind of left area, in this unconstrained paradigm to the left side of the firm capacity limits. And using advanced inverter functions, for example, we may be able to provide some level of VAR support to help mitigate some local voltage constraints. But eventually you reach a point where adding more capacity requires some level of active power management or real power curtailment. And depending upon the particular type of control scheme used, you may have various amounts of curtailed production. And so it's really this managed operation paradigm where flexible interconnection agreements are binding. So if you move to the next slide, there are a number of different control techniques that can be used to support flexible interconnection arrangements, and they mainly depend on the level of complexity of network constraints that need to be alleviated for a given situation. So the simplest form of control, which is used for really specific and fixed constraints, are time capacity connections. So these can be used when there is a series of temporal constraints that don't change over time but are applicable to a specific DER customer as part of their interconnection agreement. And an example of this would be a schedule-based capacity limit that perhaps varies based upon the season of the year. Second, if we're really looking at simple localized constraints for a specific, for example, a specific line that is close to its thermal limit, there may be several other control techniques that can be used, including export limiting devices, if the primary use of the DER is to serve, say, local load, local management schemes if constraints are close by the DER, or even remote intertrip schemes if there's a distant constraint to be monitored, such as reverse power flow at the substation. And then lastly, if we're really talking about more complex situations where there are multiple constraints, sometimes interdependent constraints, then more complex control and management techniques may be needed, and those can be either centralized or decentralized. So if we move to the next slide, let's take a look at an illustration of the economic opportunity for a flexible interconnection, which is really one of the main drivers behind these arrangements to avoid otherwise expensive grid infrastructure upgrades. So again, an illustration here, the x-axis shows interconnected capacity, the y-axis shows the per unit integration cost per unit of interconnected capacity. And we typically maybe don't have any type of integration cost in this first paradigm, this firm capacity paradigm based upon the existing capacity of the grid infrastructure until we reach a firm capacity limit. If we advance the slide, once you reach that firm capacity limit though, you may need to reinforce the grid, and so there may be a significant cost associated with that, and the per unit cost may decrease as more capacity is connected. So units that are just over this firm capacity limit may not be able to bear the full cost of that, given specific circumstances, whereas larger units may be able to bear the cost. If we advance the slide one more, the alternative solution is to, at the firm capacity limit, provide some amount of cost for communication and controls, again, depending upon the specific scheme that might be needed. And then as capacity increases, using a flexible interconnection agreement, you start exceeding those time-varying grid export limits more and more, increasing the amount of curtailment and thus the cost per unit of interconnected capacity over time. If you advance it again, the intersection of these two is an important concept in terms of when it makes sense to reinforce the grid. Advancing one more time, so this kind of paradigm to the left is really where flexible interconnection makes economic sense, where the cost of communication and controls along with the low amounts of curtailment make more economic sense than firm upgrades. If you advance it one more time, then this paradigm to the right is really your upgrade paradigm, where it actually may be more economic to do a firm upgrade. So again, the specifics of what this looks like vary from project to project, but this is a kind of a nice illustration to show that there is economic opportunity for these flexible interconnection arrangements. Next slide. So beyond economic opportunity, flexible interconnection can really enhance customer value. So they can offer DER customers faster and cheaper interconnection, and you can integrate more in areas with limited hosting capacity. So some of the major drivers that we've seen are, low resource costs, so areas where there's cheap and available land for solar, and then those that have particularly expensive grid-side mitigation measures and infrequent need to curtail are major drivers for successful projects. And benefits kind of fall into various categories. DER customers can have faster and cheaper connection for upgrade costs that are socialized across all ratepayers. Obviously, avoiding those can help reduce total rates for all ratepayers. And then it also helps to achieve some policy objectives related to progress towards DER penetration goals and emissions targets. So something that's of growing interest around the country and around the world. I think with that, I'll turn it back over to Kelsey and Devin, who are going to take us through some more detailed explanation of some case studies that we've been looking at over the past several years. Kelsey?
Great, thank you. So these case studies will kind of touch on a number of different aspects of what we've seen, including how much curtailment may actually be experienced in these cases, when could this potentially make financial sense, how do you assess the curtailment over time, and how does that assessment of curtailment potentially affect financing and viability of these solutions. So next slide. I think one sort of key point that we want to emphasize here is that curtailment for a lot of flexible interconnection schemes can actually be less than power loss to clipping, just due to having high DC to AC ratios or inverter loading ratios that are becoming more and more commonplace. And so if you kind of look at this figure here, this is just illustrating the concept of clipping. So it's the idea that if you have an oversized or an undersized inverter, so a high DC to AC ratio, at some points during the day, your DC energy output potential is going to increase the AC energy output potential, and you have some energy that's clipped there. And this figure is just showing that for two different DC AC ratios of 1.4 where you see clipping and 1.15 where you don't see clipping. And this obviously is a simplification that varies throughout the year. In some places, you'll have more or less clipped energy depending on how sunny it is and how often you're really operating near that maximum DC output point. Next, or go ahead and click through. And so this is just giving you a sense of sort of in the market, what types of inverter loading ratios or DC to AC ratios we're seeing over time for different types of systems, including fixed tilt and tracking PV. And you can see this has kind of increased over time. So people are more and more willing to sacrifice some of that energy during the day in the context of the overall system cost and revenue optimization. Next slide. Go ahead. So this is an example of what that looks like, what curtailment versus clipping could look like in one use case. Unfortunately, we don't quite have results. We have results, they're not quite published yet for some more coordinated flexible interconnection schemes, but hopefully this gives you some sense of what we're talking about here. So here you can see the AC output clipping and curtailment at different DC to AC ratios using the category B volt-var curve from the IEEE 1547 standard. And what you can really see is that in this case, the curtailment is very minimal, whereas the clipping can be somewhat significant, up to a few percent of the DC output over the course of a full year, depending on that DC-AC ratio. And while the clipping here is very low for volt-var controls, we've also seen in a lot of cases that, you know, you can have a more coordinated flexible interconnection approach where you also have less than a few percent of curtailment. And so it can be either on par with or even less than the clipping that you might otherwise experience anyway on your system. Next slide. And another thing that I just wanted to kind of emphasize here is that a lot of times the curtailment may be a lot lower than the variability you get year on year in PV output anyway, just due to weather without even a flexible interconnection scheme in place. So this is showing an example of modeled results of curtailment and then PV production without curtailment in the green for 3 different years that we looked at on a particular feeder. And this did have a more kind of coordinated flexible interconnection scheme. And you can see that the variability and the total magnitude of curtailment is much less than just the uncertainty overall and how much PV production you'll get out of a particular system. Next slide. But I think there's a few important things to know. So even though we've kind of seen in a lot of studies so far that you can have this relatively low amount of curtailment with flexible interconnection in a lot of scenarios, there's a few caveats to that. And one of them Stephen touched on earlier, which is that this is really kind of a case-by-case basis what the economics look like, and that'll change at different penetration levels. So for a particular feeder, it may be, you may have really expensive upgrades that you would have to pay for with traditional interconnection, firm interconnection, and so curtailing a little bit makes perfect sense economically at a certain penetration level. But even in those cases, once you get up into higher penetration levels, or as things change in the future, so that can be the grid, loads, or in particular the deployment of other PV that may or may not be in a flexible interconnection scheme, that can increase the curtailment and potentially push you into that uneconomic curtailment zone at some point. And there may be other cases where really you just have a very cheap firm interconnection upgrade, like changing the settings on a voltage regulator, for example, and are willing to pay for that rather than accept the uncertainty around the curtailment risk. So I think when you're thinking about flexible interconnection and trying to evaluate that as an option, it's really good to look into the future in terms of what the curtailment could look like under these uncertainties about how loads and weather and other PV or even other DER deployment could change over time. And a lot of this really also depends on the details of the control scheme. So trying to think about not just the algorithm, but how does it behave if there's a communication downtime? If there's a constraint, is the PV completely curtailed, or is it just step back in discrete increments until the constraint is resolved? And making sure to reflect some of those factors in the analysis. And a lot of times these aren't really considered today. Flexible interconnection is pretty new, but in the future, continuing to think about robust or replicable and kind of transparent methodologies for assessing these risks is important for assessing the cost benefit of moving to a flexible interconnection, and then also increasing confidence in the curtailment levels or sort of value at risk of curtailment in terms of potential revenue loss, which can help to support financing of flexible interconnection projects, which we've heard can be challenging if there is uncertainty about that curtailment risk over time. Next slide. Okay, so with that, I think I'm going to hand this off to Devin to go through some of the case studies that they've done at EPRI on flexible interconnection.
Thanks, Kelsey. This is Devin Van Zandt at EPRI, and I'm involved in the grid impact studies related to DER. And I'm just going to walk through one example of a study we performed. It's a good segue, I think, from what Kelsey is just mentioned about some of the caveats in terms of doing studies and how one of the key things that we've heard is that in order to finance projects, there needs to be some level of certainty as to how much curtailment would exist, because obviously that gets translated into dollars. So the assumption here is that you've gone, you've looked at a number of different options, and this is just another option in the toolbox. And what we were trying to evaluate was what is the level of curtailment for a number of different scenarios. So in this study, we looked at 5 different feeders with a range from 4 to 15 kilometers in length, with a variety of cap bank and line regulator configurations from a voltage regulation standpoint. The goal was to select enough feeders and locations to draw generalized conclusions. So we actually studied the flexibility at every node in each of these feeders to draw upon to create a large data set essentially for us to look at. In this case, we looked at time series analysis, so we're performing hourly simulation to analyze the flexibility at each of those nodes. If you go to the next slide, Nada, please. So as Kelsey and Stephen have mentioned, the coupling of hosting capacity and the time-varying nature of a hosting capacity is a very important component of the flexibility that exists at a particular node within the system. The correlation of load and PV, in this case, we were looking at PV alone for our DER. The correlation there is a key factor. So highly correlated load and output can have a significant impact on flexibility. What we did in this study, we also did some sensitivity analysis where we analyzed different load and PV radiance profiles from the Southwest, the Midwest, and the Northeast to compare and contrast those. One of the findings, which we anticipated, was that the less variability in the solar radiance, the less actual flexible capability there is, meaning you had a lower, what we would characterize as a FICS, we call it a FICS 90 in comparison to other locations. So places where there's a high variability, led to higher flexibility. If you go to the next slide, please. So as Kelsey was sharing earlier about dynamic hosting capacity, part of our process here was to actually calculate the hosting capacity over the course of a year at every node in each of those feeders. We were looking at overvoltage on the medium voltage system and then thermal loading. We did not consider protection-related issues. We also did not consider the low voltage system, and overvoltage might occur there. As Kelsey said, these are sort of caveats in terms of you may have a system conditions that are not acceptable, and so those would have to be baked into the hosting capacity analysis that would be performed on an hourly basis. Typically, when hosting capacity is used, you choose the minimum hosting capacity or the sort of the worst case scenario, or you look at the min load and max load. In this case, you really do need to look at the time varying hosting capacity across a full year. That is really an essential part to actually calculate the amount of curtailment over the course of the year. Another caveat, I think, to doing this modeling work, and part of our research is really to develop methodologies that would lead to an acceptable outcome where projects could be financed based on the analysis, is the variability, as Kelsey was mentioning, in terms of weather, irradiance, load. We know those are going to change over time. And so in this work, we were looking at single load forecasts, single irradiance profiles, and going forward, those are going to need to be probabilistic in a sense so that we actually assess and we look at the bookends of these types of analysis. And that's going to be really what's important for financing projects in the future. If you go to the next slide, Nadav. So as I mentioned, what we did was we calculated at every node, and we just walked through the feeder at every node along the feeder. We calculated the 8760 hosting capacity values, assuming looking at thermal and overvoltage constraints. And what that creates is the curve to the right, which is what we call the FICS analysis results. And our focus, because there are so many data points here, was on what we called FICS 90, and I'll describe that in the next slide. But basically, that is the range of flexibility across a feeder. In this case, this feeder has quite a bit of range of flexibility from basically around 1.3 per unit to at least at 90%, at 10% curtailment to around 3.5. So if you looked at any point in that feeder, it says that the range of size that you could increase the DER to is around 1.2 to 3.5 for 10% curtailment. So it says there's a broad range, and it depends on the location with respect to the substation. It depends on if it's a lateral. So there are a lot of things that have a significant impact on the flexibility. If you go to the next slide, just to drive home this point a little bit further, the graph on the left is two different feeders and at two different locations on the feeder. So you can see the blue line shows that you can increase your flexibility. Your FICS 90 is around 1.3 per unit. In comparison to the uncurtailed annual production. The reason we say uncurtailed production is because we know that the solar PV plants will vary over time. It's not just a fixed generation source. So we're looking at what is the uncontrolled profile versus what's the curtailed profile. The orange feeder and location show about a 3.1 per unit increase in this FICS 90 value. So FICS 90 is just essentially our way of measuring this 10% reduction or curtailment from the uncurtailed values. The slide to the right shows the FICS 90 for a different feeder, and it shows how the variability is much less than the feeder that I showed on the earlier slide. So there is a very wide range of results. And what this tells us is that we need to perform broader analysis on broader sets of feeders and also looking at broader sets of load profiles and DER output files, really to draw better conclusions. If you go to the next slide. As it turns out, when you look at this on a feeder, and this is another example, this is, I think, the same feeder that was 2 slides before, is that typically those locations that are thermally limited are on the left-hand side of the chart on the left. And then those that are voltage limited are on the right-hand side. And that's typically, you get a tight cluster of thermally limited locations. On the right-hand side, that is actually an image that shows the feeder, and from the substation, which is on the far left at 0.000 to near the end of the feeder. The color coding is if it's orange, it's thermally limited. If it's gray, it's voltage limited. The size of the bubble is essentially the amount of flexibility you have. So you can see on the laterals, you have very limited flexibility, and most of those are thermally limited. As you move away from the substation, you have the system is a little bit less stiff at those locations, so you have more voltage limitations that show up, and you have broader flexibility because you have broader variation in your hosting capacity. The image on the right hand there is just to show, okay, potential control options that you might implement, as opposed to just control management, the potential to put autonomous functions there. So that was just to kind of show how this might be actually viewed for developers. Next slide. Oh, sorry. So we studied over 1,300 locations across those feeders, across those 5 feeders. We saw very, very broad variability, across all of those feeders. And what we tried to do is try to come up with some methods to draw more generalized conclusions here. So we charted out this fixed 90 point. So this is that 10% of 10% curtailment off of the uncurtailed value on the y-axis, and on the x-axis is the average hosting capacity across the year divided by the minimum hosting capacity. So that's essentially a measurement of the flexibility, or at least the variation in hosting capacity. And as it turns out, that each of the feeders that we looked at, there's a very, very high correlation between the fixed 90 and the average hosting capacity divided by the minimum hosting capacity. So what this may lead us to, instead of performing computations at every node in a feeder, which is what we had done in this example, is we can spread that out and perform it all across a much fewer set of nodes and draw conclusions based upon these types of correlations, and there's a linear relationship here. As a point to note, the analysis took quite a bit of time. So we would, for a 400 node feeder running on a single core, this could take days to run the 8760 analysis. So it's really critical to take that runtime down by applying good logic around reducing the solution space. I think I'm handing off the next slide to Stephen. Is that correct?
Yeah, thanks, Devin. So, yeah, we want to kind of spend the rest of the time kind of summarizing some of what we've learned, some of the key challenges related to flexible interconnection, and some ongoing research that we have in place before opening it up to questions from the audience. So if we go to the next slide, EPRI and NREL have been tracking a range of projects demonstrating flexible interconnection. And you can see from this table there are several out there already. It may be a little bit outdated, but you can see projects that have been in service for some time, while others that are out there that we are aware of are still in the design or commissioning phase. And these projects cover a range of locations, many of them from various parts of Europe and some emerging here in the United States. And I'm not really going to go into detail on all of these, but do want to point out a couple things related to these projects. And that's that no one project is really the same. They all use different management solutions, manage different types of constraints, and different DER types. So there's really a range of possibilities that flexible interconnection can really apply to at the distribution level. If you are interested in learning more about these projects, we do have some references at the back of this presentation, so I encourage you to look at those where we review them in more detail. Also, many of these projects have produced their own publicly available reports, and you can find those using a quick Google search. So they're here for your reading pleasure. So next slide. Through our review of many of these kind of early adopting projects of flexible interconnection, we've learned a number of things related to kind of key learnings associated with success and some emerging requirements related to flexible interconnection. So one of the key success factors that make ideal situations for these arrangements is when you have a challenging network constraint combined with strong demand for new DER. So if you don't have a challenging constraint or one that can be easily addressed using conventional firm network reinforcement, then it often makes just more sense to go with the firm interconnection solution. Second is that several utilities who are exploring these arrangements are using heat maps to signal where there are opportunities for developers to connect using a flexible agreement. This can help provide high-level signal of the amount of curtailment that developers might expect, and can also help raise awareness of this as an option going forward. Third is that engagement with stakeholders and project developers is really a key to success for these agreements. This is new to many different stakeholders, so ensuring that they all have a good understanding of how flexible interconnection works and how much curtailment they can expect is really important. Many utilities who are early adopters of flexible interconnection have organized dedicated teams to really focus on these agreements to help maximize the engagement with the various stakeholders associated with them. Another important consideration is really ensuring visibility and transparency in the process, particularly around dispatch rules. This can be particularly important for project financing, reducing developer uncertainty, which is really one of the most common reasons for unsuccessful interconnection projects that may have otherwise been economic. In terms of solution components, it's important to really work with regulatory bodies to agree on what the predetermined dispatch algorithms are, which really dictate how curtailment will occur and what the rules are. This is particularly important for more complex arrangements involving multiple DERs contributing to perhaps multiple constraints on the system, where the rules governing who gets curtailed when can really change project economics. I also want to mention that these arrangements always require fail-safe modes. So in the case of communication loss, to really ensure reliability and power quality, having some fail-safe measure is important to make sure reliability and power quality is maintained. The last thing I want to touch on here is that flexible interconnection can and has been used as a stopgap solution to help allow customers connect more quickly while they wait on conventional network reinforcement. So for example, large projects that maybe would otherwise require a dedicated feeder could connect more quickly with a flexible interconnection arrangement while they wait on that traditional reinforcement to provide that firm interconnection. We go to the next slide. So in summary, we want to just point out that flexible interconnection can provide a good opportunity for low-cost integration of PV, especially when traditional infrastructure upgrades are otherwise would be high, and that in a lot of the scenarios that we've seen and implementations we've seen, curtailment can be low and often even lower than what clipping losses would otherwise have been, to hopefully help mitigate developer concerns about potential curtailment. However, we are still working on addressing frameworks for analyses that kind of better fully characterize and understand the amount of curtailment risk that there is going to be over time. So stay tuned. We've got more publications forthcoming and research in that area. And then also just wanted to point out that there are several flexible interconnection projects coming online in the U.S. And that many of them today have been implemented more widely in Europe. Next slide. So some of the challenges still that remain related to flexible interconnection, they can kind of be grouped into various stakeholder groupings. So for utilities, obviously these new arrangements may require revisions to conventional interconnection methodologies and require some additional analyses that they aren't familiar with. So streamlining what those could look like can be important. Obviously, providing additional resources to increase visibility, communication, and control, which may not be available, can be an important success factor. And third is anytime you start controlling, communicating with distributed devices, cybersecurity is always a concern. And then just in general, having additional field demonstrations can help increase confidence across all stakeholders in the success of these projects. From the developer standpoint, perhaps the largest challenge is really trying to understand the financial risk of curtailment, given that's where their revenues are made from. And so this is really important to help get projects financed. So more studies, more transparency around potential curtailment is an important success factor there. And then from a regulatory standpoint, helping work on what contractual agreements are going to be related to the principles of access or the rules associated with curtailment is important, and then the associated payment and compensation of what the tariffs are. And then related to that is, rules around what utilities are obligated to take with respect to exports beyond their conventional firm hosting capacity limits. And then in general, across kind of all stakeholder groups is just general education on the opportunity and the challenges associated with that. So we are hoping to address some of that in this webcast here, but there certainly needs to be a lot more out there in the industry. Determining which circumstances lead more towards stopgap measures versus those that are more enduring solutions can also be a challenge. And then as Kelsey and Devin mentioned earlier, just the availability of data and the quality of data with respect to distribution systems, the loads, and solar in and of themselves can really go a long way to helping ensure some consistency with respect to curtailment estimates. So obviously getting high quality data is always a challenge. I think with that was my last slide. I think I'll pass it to Kelsey on the next slide, who's going to talk a little bit about some ongoing research areas related to flexible interconnection.
Great, and I'll go through this really quickly because I want to leave some time for questions, but here are just some ongoing research areas we have at NREL. So we're trying to do some analysis around replicability, so trying to repeat curtailment analyses between groups that may be kind of approaching this in a different way so that you can get a sense of potential risk depending on who does the assessment and the approach that they take, as well as just in general kind of more robust curtailment risk assessment methods. And also trying to look at, and so this is somewhat similar to what Devin talked about earlier, but trying to just understand like more broadly what is the opportunity for firm versus flexible interconnection. So I think there's work at both EPRI and NREL on this topic. trying to look at the sensitivity of curtailment and hosting capacity to this data quality and resolution issue that we talked about, and then continuing to track some field projects in order to get more data validating these approaches and hopefully increase confidence in them. And then there's a lot of other work at NREL as well, just trying to develop control schemes that may be feasible for flexible interconnection involving multiple different DER. Next slide. Great.
Great. Thanks very much, guys. Appreciate the presentation. And now we're going to segue into a Q&A session for our remaining 10 minutes of the hour. We're going to audible a little bit here, given the number of people on the webinar, and ask that if you have a question that you please submit it to us via the WebEx chat console, and then our subject matter experts will be able to answer them one by one. And depending on the volume that we receive from you, we will try and address them here today and now, or perhaps if there's too many for us to get to, we will follow up on them and send you an email. So are there existing questions that folks have submitted over the course of the hour?
Yes, and I can answer a few of them. So, and I think everybody can see them hopefully on the chat. One question was, how long does it take to run a feeder? I mentioned this briefly during the presentation. It does take, it's a lengthy process to cover every node. We were running them on single core, so we're looking at, it should be parallel, they should be able to be parallelized. So we can cut that runtime down significantly, but I think more importantly, we were looking at every node. I think that can be trimmed down. This was our kind of initial stab at looking at a broad set of nodes. So part of the rationale was to look at every node, and then this year we'll be cutting that down significantly. Michelle asked a question about using Drive, and there is a potential to use Drive. Drive would be somewhat of a simplification of the 8760 analysis, and in fact, we've done this. Yes.
If you could, for those of you of the folks on the phone who are unfamiliar with Drive, can you just briefly qualify it?
Sure. Yeah, I apologize. Yeah, the EPRI Drive tool is a model for calculating hosted capacity very efficiently. So it's far faster than sort of your classic hosting capacity tools. What Drive typically does, it looks at hosting capacity at min and max load periods. It is possible to feed Drive more load periods, and so you could theoretically run, say, at 20 different load periods and and then create basically a proxy for time-varying hosting capacity. And we have done this, and this may be something that we actually choose to do to improve the efficiency of the modeling going forward, using Drive for the purposes of calculating the time-varying hosting capacity, which then feeds into this curtailment analysis. I think there are a few other. I know Dean. Sorry, do you want to go, Kelsey?
Oh, sorry. I was just going to say there were questions from folks about autonomous control versus needing to have coordinated active control. I think I can speak to those if you want to do that. Perfect. Real quick. You can hop in if there's any other thoughts. So I think the way we've defined flexible interconnection, a lot of times we've been talking about it as this coordinated active control. But of course, in practice, you can also have autonomous control. So volt-var and volt-watt were asked about by several people here. Volt-watt and volt-var, both in studies that we've done, and I think at EPRI have done as well, have a pretty limited amount of curtailment. For volt-var, typically less than 0.5%, and that's actually bounded by the configuration of the inverter, and for volt-watt, still less than 5% or even 1% for most of those systems. So you can definitely use those to expand the hosting capacity with a pretty low curtailment risk. But we have seen that without that coordination, there's a limit to how much the hosting capacity can be expanded before you would need either another control solution or a traditional upgrade. So it's just when you have that coordination, you can kind of infinitely expand the hosting capacity at the trade-off of the economic loss due to curtailment. But the other cases that are autonomous, it's a little more limited, but obviously lower upfront cost and a little bit more simple to implement. I don't know if you have any questions, Devin, or...
Yeah, no, that's. I think you covered it well. Dean asked a question here, which is a good question that I should have brought up during the conversation, during the discussion about multiple customers that are connecting. So after you connect the first customer, the presumption is that customer has taken up some of that flexibility, and therefore the next interconnecting customer has less flexibility. The analysis that we performed was purely a nodal analysis, so it didn't assume that there were other future interconnects. What we are planning to do is something that's similar to the classic hosting capacity analysis, is where you assume a future build-out of PV on the feeder, and use that as a proxy to define sort of what I'm calling zonal flexibility. So the zonal would be at a feeder level. There would be some sort of assumptions in how the PV will build out over the feeder, and you might have small distributed PV versus several large PV. So that's something that we will be looking at in the future, but we didn't consider in this particular analysis. It was purely a nodal analysis.
The other thing I'll mention, Devin, on that question related to total feeder connection capacity and what happens after the first customer connects and then additional customers connect after that, and how does the risk of curtailment, how is that imposed on different customers? That really gets back to what I was talking about earlier on principles of access and trying to determine those rules up front, particularly with regulatory bodies. One of the kind of two primary ones that have been used in projects that those exist in are what's called last in, first out. So the last customer in is the first customer that gets curtailed, and that really protects the first customers who enter into the flexible interconnection agreement and puts more of the curtailment risks on the later connecting customers. Other arrangements are done more kind of uniformly based on total capacity at the time of connection. There are pros and cons to each of the different methods, but that's something that really needs to be established up front with regulatory bodies. Another question here was about reduction in cost and interconnection timeline, and wanted to have a little better sense of what their existing projects were for speeding that up. So again, that very much depends on what type of conventional network enforcement's needed and the specific nature of what timeline that is. But in some of the projects we've seen, conventional upgrade may take 6-9 months, even a year to actually get in the ground and get the facility interconnected. And by using a more temporary flexible interconnection agreement can streamline that to just a couple of months while they wait for the larger project. But again, very much depends on the specific nature of the project. And some of the reports that are shown at the end of this webcast, which I think will get distributed, go into more details on those for some of the projects we've profiled.
Cody asked a question about control versus management versus autonomous control. And essentially, the way I see this is that autonomous control is the first line of defense before you get to management. I see there's a sort of a hierarchy of solutions, and this is after you've assumed that your autonomous control no longer has the capability to sustain a larger interconnection. So that's really the kind of the underlying assumption when we're talking about management here.
Great. Thanks very much for the lightning round on questions, guys. We've just arrived at the top of the hour, so I want to thank all of our presenters for their time today. We hope that you've enjoyed the information that we conveyed over the last hour. As was referred, we have a number of publications at EPRI that are largely available both to members and the public. You can see them here. And you can download them just by clicking on the associated report numbers at the EPRI.com website. NREL is also working on this topic to a great degree. I know that, Kelsey, you had mentioned that there are a number that are actually in the midst of peer review, so those will likely be released shortly. In the meantime, please stay tuned to receive information from us about future DGIC events in the form of webcasts, as I mentioned, workshops, and future reports. We'll be sharing a calendar once that gets put together in the near future. And in the meantime, again, I encourage you to visit the DGIC website, sign up for the newsletter to stay connected, and provide us with some feedback on some of the areas of research inquiry you'd like to see the DGIC explore. But for now, we'll say sayonara, and thanks for joining us today. Have a great rest of your day.
One quick question. We will have, do we have the contact information for those questions we weren't able to answer, right, Amy? So we can respond via email?
Yes, that's correct.
Great.
Thank you, Devin.
Okay.
I should have mentioned that. Yes, I apologize to those folks who had submitted questions we didn't have time to address. We will follow up with you directly on those that were not addressed during the hour.
Great.
All right. Well, without further ado, thank you very much, everyone, and have a great rest of your week. Take care.